Welcome back to lecture 7 on Riemannian symmetric space. First of all, I want to give a definition of Hermitian form. So definition, let V be a complex vector space. A map from H from B cross B to C is called a Hermitian form if it satisfies the following properties. First, H of alpha U plus V comma W is equal to alpha bar H of U comma W plus HB comma W. U V W belongs to V. H of U comma alpha B plus W is equal to alpha H of U comma V plus H U comma W. H U bar is equal to H B U. Okay. A Hermitian form is called non-negative if HB comma V greater than or equal to 0 for all V belongs to V, and positive definite if HB V comma V greater than 0 for 0 not equal to V belongs to V. Remark, a positive definite Hermitian form on V is precisely an inner product on V. This Hermitian form is nothing but which satisfies all the properties of inner product except this fact that it is positive definite. Okay. So you will come back to this later, but now let us clarify some 2-3 points from the previous lecture. Okay. So first observation. So let G be a matrix Lie group. And G be its Lie algebra. Now you know that exponential map from G to G is continuous. Now this set is connected because exponential map is continuous. Okay, so therefore it will lie inside a connected component of G. Okay. So this implies exponential of G.
What did you say?
Since exponential map is continuous and Lie algebra is connected, therefore exponential of G will lie inside a connected component of G.
Okay.
Okay. Now exponential of 0 is identity. So that means that it will lie inside G naught. Connected component of identity. Identity in G. Okay. So this is clear. Now also you can one can check that G naught is also a Lie group because G naught is closed in G, and by Cartan's theorem G naught is also Lie group, and by similar exactly the same argument which I told you, that you can say that Lie algebra of G naught is equal to same as Lie algebra of G. This is the same thing at G. Okay. So this observation is important. Remember this thing. Okay. Now we have seen that for whatever groups we have discussed, we have obtained a polar decomposition, and polar decomposition is useful for seeing the group is connected or not, or more later we will also see that it will be useful in calculating the fundamental group, which is a very important topological object. Okay. Now for that we have we have seen that this notion of pseudo-algebraic group is very useful, and for that we have seen that. So let G be a pseudo-algebraic group.
Excuse me.
Yes.
May I ask a question?
Yes. Yes.
Yeah. This connected component business that you just now described. So yes. I understand that determinant can be an example where you have like non-trivial connected components, like determinant 1 matrices or so on. Are there other examples which do not arise due to these determinant considerations where a matrix Lie group has actually more than one connected component?
No, I am not getting your question.
Can a matrix Lie group have multiple connected components which are not due to determinant conditions?
Not due to determinant condition. Okay. I do not. I have no example now.
Okay.
I don't have any example now.
Okay.
No, see, you take some disconnected group and look at direct products.
Yes.
Sure. Yeah.
Yes. Okay. So this question.
Okay. Thank you.
Okay. Sorry. Okay. I think he clarified that question. Okay. So let's G be a pseudo algebraic group, and G is closed under conjugate transpose. Then the polar decomposition of G is the polar. G is equal to G intersection UN and e to the power Hn intersection G, where G is the Lie algebra of G. G is equal to Lie algebra of G. Okay. So the thing is, this condition G is closed under conjugate transpose, also a very important condition. Okay. Our focus should not be on just only pseudo algebraic group. G is closed under conjugate transpose. This is a very crucial condition. You will see that later actually, because due to this condition, we will be able to produce example of so-called Riemannian symmetric pair, and that will give us a lot of example of Riemannian symmetric space. Okay, so this condition is important. Now this pseudo algebraic group and closed under conjugate transpose is a very sufficient condition to get the polar decomposition. But that doesn't mean that if the group is not pseudo algebraic group or G, then you cannot have that polar decomposition. For example, consider this group, this GL plus NR. Okay, so A belongs to GL and R. Okay, so that determinant of A is positive. Okay, if you look at this description, it is not clear GL plus NR is pseudo algebraic or not. Okay. At present also I don't know the answer whether GL plus NR is pseudo algebraic or not. But the thing is, I have proved a polar decomposition of this group GL plus NR. GL plus NR is, this is SON into e to the power Sn, where Sn is the real symmetric matrix. So that X is equal to S transpose. Okay. So, and from here actually we can this relation is very crucial to calculate fundamental group of GL plus NR. Okay. Similarly, this group actually I have sort of SO P naught comma Q. This G belongs to SO P comma Q. So the determinant of GS is greater than or equal to 1. Determinant of G tau greater than equal to 1. This is from the very definition. It is probably not clear to me that clear why this, whether SO P naught comma SO naught P comma Q is pseudo algebraic or not. Okay, but you can get a polar decomposition. Okay, so and now we have to do that. So this is actually into this. So let G belongs to, sorry. So let G is equal to SO P comma Q. G naught is equal to SO naught P comma Q. Okay. Now let G belongs to G naught. This implies G belongs to G. Okay. For SO P comma Q group, we have the polar decomposition. I have discussed that because it is pseudo algebraic and closed under conjugate transpose. Now, as G belongs to G naught, as G belongs to G by polar decomposition of G, G is equal to some U e to the power x, where U belongs to G intersection UN and X belongs to Z. Okay. So now, so since X belongs to G, this belongs to G naught e to the power x. Now G belongs to G naught. So that will imply that U belongs to G naught. Okay. So I am getting that G naught is equal to G naught cross intersection UN cross e to the power HN intersection. Okay. So we have the polar decomposition for G naught. Okay. So now the thing is, so from here actually, what mostly we are interested in this thing. Pi 1 of G naught is equal to pi 1 of G naught intersection. Okay, it will be useful in later. So now propose, okay, so let us proposition. This SO naught P comma Q intersection U P plus Q. This is equal to SOP cross XOQ. What do you mean by that? That means I will take A0, 0, B, so that A belongs to SOP, B belongs to SOP. Okay. Proof is very clear actually. So let G belongs to, this is SO naught P comma Q intersection UP plus Q. Now I have shown that this is okay. So this implies G belongs to SO naught P comma Q. Sorry, G belongs to SOP comma Q intersection UP plus Q, and this was really SOP cross OQ. And what was the definition of this SOP? This is A0, 0B, so that A belongs to OP, B belongs to OQ, and determinant of A, determinant of B is equal to 1. Okay, so this is something. Now, okay, so as sorry, this implies G is of the form A0, 0B, so that A belongs to OP and B belongs to OQ. Determinant of A into determinant of B is equal to 1. Now we have also this condition G is equal to SO naught P comma Q This implies by that condition determinant of A is greater than equal to 1 and determinant of B is equal to greater than equal to 1. So look at this condition. A belongs to OP and determinant of A greater than equal to 1, then means A belongs to SOP. And look at these two conditions. So this will imply that B belongs to SOQ. So that means G belongs to SOP cross SOQ. Conversely, if G belongs to SOP cross SOQ, so G will be of this form A0, 0B. Okay, and this by definition this belongs to SOP cross OQ, and this is equal to SOP cross OQ is equal to SOP comma Q intersection UP plus Q. Now, as determinant of A is equal to 1 is equal to determinant of B, then this implies G was already SOP comma Q. This is the G will be SO not P comma Q. Okay. Now G belongs to SO not P comma Q, and this was already U plus P plus Q. So this implies G belongs to
Is there any problem?
We are not able to hear.
Yeah. Pritam, you have his number, right? Mobile number? Pritam? What is happening?
Where is Pritam?
I think Pritam got disconnected. He is there. I can't see him, but not responding. Pritam, can you hear us? Let me try the chat box.
Yeah, let me call to Munna maybe. Yes.
Yeah, you just call him.
Why I'm not able to call him?
Okay, I'll
I can't find his number. Strange. Oh. Hello? What happened? Some problem with internet? Hello?
So has anyone contacted Muna by phone or?
I'm calling him. Hello?
Okay, I can also call him if needed.
Oh, he said, okay. He says there is some internet problem. He will join. Okay.
So we are not comfortable with the team also. This team. I have to go out many times, rejoin.
Munada will join in a minute. He has some internet problem right now.
Can anybody hear anything? Or am I disconnected now? Is anybody here?
Yeah, Munna hasn't joined yet.
Oh.
Everyone else is there.
Yeah, Munada is having some problem with his internet. He is trying to join, but he is not able to.
Tell him to use mobile hotspot.
Yeah, Munada. So are you using HRI's Wi-Fi or your mobile hotspot?
First I used HRI's Wi-Fi, then I am now using this hotspot.
Is it working, Geo?
Geo is not working.
Yeah, Geo is not also working.
Anybody is not working.
Yeah, Munada said he won't be able to join today. So unfortunately, we have to stop.
Friday, is he going to lecture on Friday? Friday is a holiday.